Okay, so prove that this infinite sum, this is an infinite sum over all the infinitely many positive integers, prove that it's 1. Okay, well, what is the definition of this? Well, it is the limiting value of the sequence of partial sums if it converges. Okay, so need to show the sequence of partial sums converges to 1. And it asks us to use the convergence game. That means we need to show that for every d, there exists an n such that going past that index implies that our sequence of partial sums is within d of 1. And this is a positive number, and this is an index natural number. Natural number. Okay. So first we need to just get the sequence of partial sums. Here we would call this maybe Cn, so that this sum is the sum of the Cn's. But then the S sub n's are what we need. So the first thing we'll notice is that Cn equals 1 over n times n plus 1 can be split. This is a common denominator. Secretly, this wants to be a common denominator of something plus something here and here. Okay? Now, if you cross multiply and you can figure out and actually find equations that show you what a and b are, or the other method is you can guess and hope that you are right. So let's see if that's right. So I can check this by multiplying, by finding a common denominator and then adding these fractions and seeing if I get this. Okay, so n plus 1 minus n. Yep, works. So note that C sub n equals this. Then, S sub n equals, I could call this little m, but I'm going to call it little n because it doesn't matter, is equal to 1 over 1 plus negative 1 over 2. That is C1. Okay, let me just do this a little bit easier for you to follow. 1 plus C2 plus C3 plus dot 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 up to plus Cn. This is the nth partial sum. It means we add up the first n terms from this infinite sum. Okay, well, what's C1? C1, as I plug in n equals 1 there. Okay, and now you see why I should maybe call this little m, because we have n's here, and it could get confusing otherwise. But remember, this is just naming conventions, so we just have to figure out what's going on. If I plug in, I'll get 1 over 1 minus 1 over 2. That's C1. What is C2? What is C2? What's C2? It's plug in a 2 minus 1/3 plus plug in a 3 minus 1/4 plus plug in an m minus 1m plus 1th. Okay, and now notice, this cancels this, this cancels this, this cancels something there, something here is going to cancel that. And all of this is just 1 minus 1 over m plus 1. Therefore, we have an explicit formula. S sub n is equal to 1 minus 1 over m plus 1. But the harmonic sequence 1 over m goes to 0. So then also this sequence, which is the harmonic sequence except just shifted, also goes to 0 and converges to 0, so that S sub m converges to 0. Now, they wanted us specifically to use the convergence game. So what we would say is that, okay, so choose D, then look at S sub m minus 1. And we'd like to say that that is less than D. And what is it? Well, S sub m is 1 minus 1 over m plus 1, and then a minus 1. So that the 1 and the minus 1 cancel, and I just get minus 1 over m plus 1, absolute value, which, choose capital N so that 1 over n plus 1, because remember, this is just going to be absolute value of a negative number will just give me 1 over n plus 1. So that 1 over n plus 1 is less than D. Then n greater or equal to capital N means 1 over n is... No. What am I talking about? 1 over n plus 1. I guess I was calling these by m's, so maybe I'll call this m, 1 over n plus 1, is less than 1 over capital N plus 1. Because we chose little m greater than capital N, this fraction is smaller than that fraction. But we know that we chose capital N so that this is less than D. Okay? Thus, m greater than capital N implies that S sub m minus 1 is less than D, and we are done with our proof. The sequence converges to 1, and we used the convergence game. Here was the convergence game. Here was sort of like why we knew that this was going to work. We're essentially doing the convergence game for the harmonic series again, or harmonic sequence.